Hi, this is an explanation for problem number 64 in chapter 11. Number 64 reads, an engine does 10 joules of work and exhausts 15 joules of waste heat. Now part A asks, what is the engine's efficiency? Now for this question, we're going to use a thermal efficiency equation that reads, thermal efficiency is equal to Q1 minus Q2 divided by Q1. Q1 is the heat source from the hot source. Q2 is the heat absorbed by the cold sink, which in this case we were told in the problem is 15 joules because that's the waste heat. And then work is the amount of work done, which that's pretty straightforward, which we're also told that, which is 10 joules. Now, work is actually equal to Q1 minus Q2. And so if we're given work, which is 10 joules, we're given Q2, which is 15 joules, adding those two together will give us Q1. And so 15 plus 10 is 25. So now our equation can go from Q1 minus Q2 over Q1, be simplified down to W over Q1, which we solve for Q1 down here, 25 joules. So now we already have work, 10 joules divided by 25 joules equals 40% efficiency. Now part B is asking, if the cold reservoir temperature is 20 degrees Celsius, what is the minimum possible temperature in degrees Celsius of the hot reservoir? Okay, I'm going to have to erase part A to have more room on the board. Now we can use the same type of relationship that we used to solve for part A, but rather than for Q, we're going to go ahead and just use T for temperature. So our relationship is going to read T1 minus T2 divided by T1. Now in the problem, we're given T2 because it says the cold reservoir temperature is 20 degrees Celsius. Okay, so that's nice. We're given T2, but it's in degrees Celsius. So we actually need to convert that to Kelvin by simply adding 273, and that will give us 293 Kelvin. Well, okay, so we've got T2, but how are we going to solve for T1? The way that we do this is we're going to use the same relationship that we solved for in part A, and we're going to make it equal to this equation in part B because we actually did solve for the thermal efficiency, right? Or the thermal efficiency, right? So our ratio was 10 to 25. So we can set this equal to now T1 minus T2 divided by T1. Now if we're trying to solve for T1, now we just need to algebraically isolate T1 on one side, and then we can plug this into our equation later using 293 for T2, but we'll get there. So first off, to isolate the T1, we want to get rid of our denominator so we can multiply the left side by T1 and the right side by 25. Okay, and we'll be left with this equation right here. Now, we want to get T1 by itself. So now what we can do is we're just going to go ahead and divide by 10. Okay, I made a mistake actually. We wouldn't divide by 10 to isolate the T1 on one side because we still have a T1 value on our right side. So what we need to do is we need to multiply this through. Now that we have this, we can go ahead and simply subtract this T1 term. So now we have a negative on both sides. We can just divide by -1. Now we have a positive value on both sides of the equation. So at this point, we can now isolate our T1 by dividing by 15. So I'm going to take this equation and I'm going to write it up over here where I have a little bit more space. So now we have T1 equals 25 divided by 15, but 25 is times T2. However, we already solved for our T2 value right here. So I'm going to go ahead and plug this in for T2 over here now. If we solve for this on our calculator, we're going to be left with approximately 488 Kelvin. But our answer they wanted us to express our answer in Celsius. So now we're going to subtract 273. We'll be left with approximately 215 degrees Celsius.